Greetings! I am May Alaysa Balad, and today I'll be presenting a study by Leo et al. 2025 entitled Magnetic Monitoring and Source Traceability of Heavy Metal Pollution in the Urban Topsoil of Xuzhou, China. This study will show how analyzing the magnetic properties of the soil provides a fascinating window into the sources and extent of this pollution. So let's discover how magnetism can reveal the hidden fingerprints of heavy metal contamination, leading us to a better understanding of how to tackle this environmental challenge. Xuzhou, China, a city with a long history of coal-based industry, is grappling with a significant challenge: a heavy metal pollution in its urban topsoil. These heavy metals pose a serious threat to public health, accumulating in the soil through atmospheric deposition and rainfall. Urban soils, acting as both sinks and sources, concentrate pollutants from industrial and traffic emissions. This study investigates the nature and extent of this pollution, using innovative methods to understand its sources and potential impacts. So the research area of this study is the central urban area of Xuzhou City, where the population, economy, and transportation are highly concentrated. The area of this region is approximately 660 square kilometers, and Xuzhou is crucial to this study because of its resource-intensive economy and role as a transitional ecological zone. This study aims to assess the environmental quality of Xuzhou's urban topsoil by examining heavy metal pollution and its correlation with magnetic properties. It will identify pollution hotspots through spatial analysis, trace potential sources using statistical and magnetic methods, and ultimately establish a monitoring system based on environmental magnetic technology. Figure 2 shows a systematic grid-based sampling strategy that was used to select 71 sampling points. From these, 142 samples were collected at two depths in 0 to 2 cm and 3 to 10 cm per point to study the vertical distribution of heavy metals in soil. Manual sampling was performed with a chemically inert hard plastic shovel to avoid cross-contamination. The samples were subjected to multi-point homogenization and quartering for quality control. This study employed a multi-pronged approach combining geochemical and environmental magnetic techniques. Heavy metal concentrations were determined using inductively coupled plasma mass spectrometry in the soil samples collected, and the key magnetic indicators were measured using a magnetic susceptibility meter to assess magnetic mineral content. And then, the researchers applied the geoaccumulation index, pollution load index, and potential ecological risk index to evaluate the extent and ecological risks of heavy metal contamination. Spatial analysis of the results was performed using ArcGIS 10.8, while statistical analysis, including correlation analysis and principal component analysis, were conducted using SPSS 27.0. Data visualization and further analysis were performed using Surfer 13.0, Origin 2021, and Excel 2023 to create maps and charts. This integrated approach provided a comprehensive assessment of heavy metal pollution in Xuzhou's urban topsoil. The statistical results of heavy metal concentrations in the topsoil of the Xuzhou urban area are presented in the Table 1. The mean concentrations of copper, nickel, lead, and zinc were 1.2 to 1.7 times higher than the soil background values, indicating that there may be additional heavy metals inputs brought about by human activities. The average concentrations of chromium, iron, and manganese are comparable to or lower than the background values. It is evident that the urban soil of Xuzhou City is contaminated with varying degrees of heavy metals, particularly copper, nickel, and zinc, which exhibit the most pronounced levels of pollution. And this study successfully employed the geoaccumulation index to analyze heavy metal contamination characteristics in urban soils at depth of 0 to 2 cm, which is the topsoil, and 3 to 10 cm, which is the subsoil. As shown in Figure 3, the results revealed significantly higher contamination levels of chromium, copper, nickel, lead, and zinc in the 0 to 2 cm topsoil compared to the 3 to 10 cm subsoil. The data from 0 to 2 cm soil samples are colored blue, and data from 3 to 10 cm soil samples are colored orange. And as illustrated in Figure 4, the pollution load index for heavy metals in the 0 to 2 cm soils is higher than that in the 3 to 10 cm soils at most sampling points. The distribution of samples classified by pollution levels demonstrate that 3.5% of the samples exhibit heavy pollution, and then 18.3% display moderate pollution, and a substantial majority, accounting for 66.9%, are categorized as slightly polluted. Notably, only a small proportion, which is 11.3% of the samples, are determined to be unpolluted. The potential ecological risk index results indicated that all studied elements exhibited individual ecological risk factors below 40, corresponding to a low ecological risk level. Based on Table 2, only copper and nickel showed minor proportions of moderate risk. The comprehensive potential ecological risk index further confirmed that all samples were classified as low risk. This finding suggests that from an ecological risk perspective, the heavy metals in the studied soils pose minimal immediate threats to ecosystem health. Spatial analysis of heavy metal pollution in Xuzhou's topsoil, as depicted in Figure 5, revealed a consistent pattern across the 0 to 2 cm and 3 to 10 cm soil layers. High pollution load index values were concentrated in the city center, an area with high traffic density, and the northeast, where numerous factories like cement, machinery, and chemical are located within a 10-kilometer radius. And this suggests a strong link between elevated pollution load index and transportation and industrial activities. In contrast, the southwest near Yunlong Lake showed significantly lower pollution load index values, likely due to the absence of major industrial sources and its limited traffic. The results of the magnetic parameters measured are presented in Table 3. It is evident that the values of each magnetic parameter are greater in soil from 0 to 2 cm depth than in soil from 3 to 10 cm, except for frequency-dependent magnetic susceptibility. As shown in Figure 5, it was further demonstrated that both saturated isothermal remnants and soft exhibited a significant positive correlation with low-frequency magnetic susceptibility, thereby indicating that the magnetic minerals present in the topsoil of the study area are predominantly ferrimagnetic minerals, characterized by multi-domain and pseudo-single domain. And then the previous research by Liu et al. 2007 has demonstrated that MD and PSD magnetic minerals are primarily sourced from anthropogenic activities including traffic emissions and industrial production. Correlation analysis revealed a strong relationship between certain magnetic parameters and the concentrations of heavy metals, particularly lead and zinc, with correlation coefficients ranging from 0.63 to 0.75 as presented in Figure 7. And these magnetic indicators, which reflect the presence of ferromagnetic minerals, also showed moderate correlations with chromium, copper, and iron, though at lower strengths, which is 0.23 to 0.42. Moreover, these magnetic parameters displayed significant positive correlations with the pollution load index, suggesting that they are not only closely linked to specific heavy metals but also to overall soil pollution levels. The strong intercorrelation among these parameters supports their use as effective, rapid indicators for assessing heavy metal contamination in Xuzhou's urban topsoil. To further elucidate the sources of heavy metal contamination, principal component analysis was performed on the above magnetic parameters and heavy metals. The results are presented in Table 4. So the analysis yielded a high Kaiser-Meyer-Olkin value of 0.829 and a p-value of 0.000, confirming that the dataset was suitable for principal component analysis. From these, 4 principal components were identified, explaining 83.13% of the total variance. And these components suggest the presence of 4 major sources contributing to heavy metal and magnetic mineral contamination in the study's area soil. In conclusion, Liu et al. 2025 study effectively shows that combining environmental magnetism with geochemical analysis is a powerful approach for assessing heavy metal pollution in Xuzhou's urban topsoil. The study found elevated levels of copper, nickel, lead, and zinc, especially near the surface layer, pointing to strong human influence. Notably, magnetic parameters, particularly those linked to lead and zinc, proved to be reliable, low-cost indicators of pollution. Through principal component analysis, key pollution sources were traced to transportation, fossil fuel combustion, industrial activities, and natural soil processes. Overall, the study offers a solid foundation for using environmental magnetism in pollution monitoring and urban soil management. That's all. Thank you.